Welcome to Lesson 9 of AQA A-Level Physics. Today we're going to discuss the photoelectric effect. We're going to look at the three important terms that surround the topic. We're also going to look at a bit of wave theory, a bit of particle theory, and their explanations around it. So let's start by looking at some key terms. So the photoelectric effect, we've got three key terms that we need to be able to define. We've got something called the threshold frequency. Now the threshold frequency is the lowest frequency a photon can have that will cause photoelectron emission. Work function. Now the work function is a minimum energy required to release an electron from a metal surface. And then to define what we mean by the photoelectric effect, we say that it's the release of photoelectron from a metal surface when EM radiation is incident on the surface. Now there's two important things I need to mention here. First of all, we need to include the word metal surface in both of our definitions here to indicate we know it's coming from a metal. Secondly, in our definition of photoelectric effect, we need to talk about this EM radiation being incident upon the metal surface for the marks. So that's the photoelectric effect. There's some of the key terms. Now, this experiment using a gold leaf electroscope, so we can charge up and have our gold leaf electroscope. Now, there are three conclusions that come from this. You don't need to know the experiment. The first conclusion is no photoelectrons are emitted if the frequency of radiation is below a certain value. That certain value is the threshold frequency. Anything below this frequency, there's no photoelectrons emitted. The second conclusion, photoelectrons are emitted with a range of kinetic energies. So they all have different kinetic energies. They don't have one value. And then conclusion 3, number of photoelectrons emitted per second is proportional to the intensity of the radiation. So there are conclusions and we just need to know them. Now, 3 can be explained by wave theory. 1 and 2 cannot. Now, wave theory says the following. So, wave theory tells us that if we increase the energy, we increase the intensity because it's a proportional relationship. And wave theory would tell us that every time this wave hits our electron, it gains some energy. So every time this wave hits, it gains some energy. And over time, as this wave keeps being absorbed by the electron, this electron is going to gain more and more energy each time. And when it gets to a certain value, our electron will be emitted. Well, that doesn't happen. And wave theory doesn't even mention frequency. It just says if you increase the intensity, so you're increasing the energy, increasing the power of this wave effectively, it's going to gain more energy. So it actually says wave theory that if we increase the intensity, we increase the energy, which means our kinetic energy is going to increase. All the electrons have a fixed value. That doesn't happen. So we have to have a look at it differently. Now, Einstein came along and we knew from Hertz that frequency played a role. Now, actually Hertz found out that ultraviolet caused the sparking to happen when he was investigating this phenomenon. So Einstein came along, he proposed a photon model, and in the previous lesson we said that a photon was a discrete packet of energy, and we know actually that the energy of a photon is E equals hf, so energy related to the Planck's constant times the frequency, or E equals hc over lambda, because we know the frequency is going to depend on the wavelength. Now, what Einstein proposes to us is when light hits the surface of metal, it's bombarded by photons. So these photons just keep hitting the metal surface. And when one of these photons collides with an electron, it gains energy equal to hf. Now, we've just said it has to be above a certain frequency. So Einstein brings the idea that frequency is going to play a part in photoelectron emission. So that's the photon model. So we get to this point where we can have a look at a graph and it mathematically. Now, what we find out is we get something that looks a little bit like this. Now, we have kinetic energy. Now, at zero kinetic energy, we're going to have something called the threshold frequency. So our x-intercept is going to represent the threshold frequency. Now, my y-intercept is going to represent the work function. Now, the work function we just defined at the beginning of this video is the minimum energy required for photoelectron emission. Which should hopefully be 6.63 times 10 to the minus 30. So, if we have a different metal, it's going to have a different work function. It's also going to require a different frequency of light. So we can actually draw this on. So if we have something with a higher threshold frequency, you need to be able to draw the line to represent it. Now it's just going to be parallel. And that's going to be a higher threshold frequency when we represent it. Now we come up with the equation of this. We actually come up with the equation EK max, so maximum kinetic energy, equals HF minus the work function. Now HF is the energy of our photon. So let's think about this equation. So if I've got energy of a photon and I've got a minimum energy required for my electron, my photoelectron, to be emitted. So if I have my energy and I take away that minimum energy, I get some energy remaining. And that energy remaining is going to be kinetic energy. Because in effect, the energy gained by the electron, the work function, brings it to the surface of the metal. If it's got some more energy, that electron can now leave the metal surface with the kinetic energy. So our total energy minus our minimum energy gives us the energy associated with movement. And that's a nice equation, really. However, we can rewrite this. Now, if we have minimum kinetic energy is going to be 0. Now, we can work out the threshold frequency, which I'm going to now denote F0, for our work function. This equation now becomes work function equals HF0. So my threshold frequency is equal to the work function divided by the Planck's constant. So we can rewrite it. So that gives us this value. Just talked about E equals HF and HC over lambda. Now, the photon model kind of proves this because of this. So, wave theory tells us that if we have a higher intensity, that means we have more photons. Now, why does that tell us that? Well, let's have a look at this. We know that intensity is power over area. But in earlier video, we said power equaled NHF. So number of photons times the Planck constant times F, the frequency. So that means if my number of photons increases, my power increases. Well, if my power increases, my intensity increases. So that's where that relationship comes from. Now, if wave theory was correct, that would mean that kinetic energy increased. But that doesn't actually happen. Therefore, it tells us that there has to be a one-to-one interaction. Is that for this photoelectron emission to occur, a photon gets absorbed by my electron and moves up, if it can. If it cannot move up with that, the photon just kind of passes by. If it's low frequency. If it's a higher frequency, like ultraviolet, the photon comes in, gets absorbed by the electron, and the electron moves up. My electron cannot absorb 2 photons, 3 photons or 4. It can only absorb 1. So 1 photon for 1 electron, a one-to-one interaction. So hopefully today has given you a flavour of some of the conclusions from the photoelectric effect, some of the key terms, a bit of wave theory, and hopefully I've tried to explain with a photon model how it applies and how it proves the photoelectric effect. And then we looked at the end, the graph and the associated maths.